In this session, we're going to look at asynchronous counters. In other words, counters whose clocks on the individual devices are not controlled by the same clock signal. So counters are a specialized form of memory device. They're ones that are going to count through a predetermined sequence of numbers. Doesn't necessarily mean they have to be in order, but it's going to always perform the same count. Now, as opposed to registers that just store a value for a period of time, these have a predetermined sequence that they're going to work through. The number of flip-flops that are in the counter is going to define what counts are possible. So if we have a 2-bit flip-flop, for example, we have 4 possible outputs, so we can count from 0 to 3. Now we could count 1, 1, 2, 0, 3, or we could count 0, 1, 2, 3, or we could count 3, 2, 1, 0. Any order is fine, but we only have those possible counts. So if we have n flip-flops, as we have here, that means we're going to have 2 to the n different counts, the range being from 0 to 2n minus 1. So if we have an 8-bit flip-flop, we have a count from 0 to 255. So let's take a look at asynchronous counters first. The first thing that's important to remember when we're talking about asynchronous counters is that we're going to use JK flip-flops and we're going to wire them to toggle. So we know that on every clock edge, the device is going to change state. So if it was 0, it's going to go to 1. If it was 1, it's going to go to 0. Now the interesting thing about our asynchronous counters is that the output of one flip-flop is the clock for the next. So this is where it's different from what we've seen before, because in our circuits we've looked at so far, the clock pulses have all come from the same signal. Not anymore. It's kind of a ripple effect, and hence the name ripple counter for these, but we're going to see the output from one controlling the clock for the next. So as you can see down here, there are 3 main types of asynchronous counters. It's actually the same device, same configuration that we'll look at. Sometimes it's called a ripple counter, sometimes it's called a mod counter, sometimes it's called a frequency divider, and as we go through this session and the next, you'll understand why those names are given. So here's a 2-bit asynchronous counter. So 2 bits implies that we have 2 flip-flops. Notice they're both JK flip-flops, and that the inputs, J and K, in both cases, are tied high. That means this device is acting as a toggle flip-flop, so let's put a T in there just to remind ourselves. Now a little more importantly, let's take a look at the clock. So we can see here that it's a falling edge clock, and we can see our first flip-flop is connected to our clock signal that we have down here. But if we look at the second one, we can see that this clock is connected to the output of the first flip-flop. So no longer is it going to be controlled by this signal, but it's going to be controlled by the waveform that we see on Q0. So let's take a look at how that's going to work. So let's mark in, first of all, our falling edges. We know we have falling edges for this first clock, so we're going to mark that in, but we're going to mark the edges only through Q0, because Q1 is going to be affected by Q0 edges, not the clock edges. So we're only going to drop them down part way. Now, we know it's going to toggle, so assuming Q0 starts low, we're going to come here, and I'm going to show a bit of that propagation delay, so my changes aren't going to happen right on the line. It's going to toggle every time. So we follow it up, toggling at each sample point. And we can see that regular waveform changing at every falling edge. Now if we look at what happens to our second flip-flop and what Q1 is going to look like, we have to take into account the changes in Q. So now we're looking for the falling edges in Q. So let's mark those in. So there's a falling edge, there's a falling edge, a falling edge, falling edge, falling edge. So you can see those edges are only every second time based on the first one. What's our waveform going to look like? Well, this one is also going to toggle on those falling edges. So we can see the pulses are twice as long, which means the frequency is half the frequency of this first pulse. So we're starting to see a pattern here. Now let's look at a 4-bit counter. We had a 2-bit before, giving us Q0 and Q1. Now we've added 2 more flip-flops so that we can hold values for Q2 and Q3. Before, we could count 0 through 3. Now, with 4 bits, we can count 0 through 15. What we need to do first is figure out how Q2 is going to behave. So Q2 is dependent on Q1. So let's mark the falling edges of Q1 in. Remember, we only take them down for the next waveform. So assuming Q2 starts low, we're going to change states here. Again, mark in the propagation delay. Makes it easier to make those choices as to whether something is high or low when you're sampling. So we can see we have 2 pulses for every period here, 2 pulses for every period here. So our frequency is half again. Now let's take a look at what happens for Q3. So again, we're going to mark the falling edges in from Q2. So we have a falling edge here and a falling edge here. We only have 2 of them now. And now let's put the waveform in for Q3. Assuming it starts low, we come over here. There's our transition or our toggle. There's our last toggle. So again, we can see 2 full samples for 1 period here. So our frequency has halved again. So this is where the term frequency divider comes in. The frequency of each subsequent flip-flop is half of that from before. So let's take a look at a waveform that's a little bit cleaner. Here we have the waveforms that we've just generated. We can see Q0, Q1, Q2, and Q3. And what I have done is I've shown, and we can see it probably most clearly here, I've shown the propagation delay that occurs each time. So each one's pushed out a little bit farther. The more we do, if we added Q4, 5, 6, 7, 8, for example, you're going to see that propagation delay get a little bit more each time. And if that propagation delay becomes too big, it means that we might start to miss counts. So the effect of that propagation delay is why it's called a ripple counter. But we have to be careful of that, and we have to keep our frequencies fairly low in order to accommodate that. Now you may have noticed that the title changed here, and this is called a mod 16 counter. When you have a mod 16 counter, that means you can count from 0 to 15. You might not count directly 0, 1, 2, 3 up to 15. You might count 15 down to 0, or you might count all the odd numbers first, followed by all the even numbers. But the range can only include the values from 0 to 15. So let's take a look at what this counter is counting. So when we're looking to figure out what count a counter counts through, what we want to do is sample about halfway through a clock cycle. So our clock cycles are shown here. So we're on a falling edge. So we want to look halfway between a falling edge and the next falling edge. So our first sample we would take right about here. Our next one, basically we're going to take the sample on the rising edge. So let's mark those in. And we want to go through all the way through until we start to see the waveforms look like they did at our first sample. So in our first sample, back here, all the waveforms were low. I've now returned to the point where all the waveforms are low. So it looks like I've gone full cycle. So let's figure out what we've got. So when we're reading our waveforms, we have to always start with the most significant bit. So in that case, our most significant bit is Q3, our least significant bit is Q0. So we're going to read our samples from lowest to highest here. So our first binary value is going to be 0, 0, 0, 0, which gives us a count of 0. At our next sample, we have 0, 0, 0, 1, which means we have the binary count of 1. Next one, we have 0, 0, 1, 0, which is 2. Next one, we have 0, 0, 1, 1. We have 3. We seem to be counting in order, so let's see if that pattern follows through. We have 0, 1, 0, 0, which gives us 4. We have 0, 1, 0, 1, which is 5. 0, 1, 1, 0, which is 6. 0, 1, 1, 1, 7. So it looks like we have an up counter. Let's keep going, see if we get all the way to 15. We have 1, 0, 0, 0, which is 8. We have 1, 0, 0, 1, which is 9. We have 1, 0, 1, 0, which is 10. Looking good for that up counter. We have 1, 0, 1, 1, which is 11. 1, 1, 0, 0, which is 12. 1, 1, 0, 1, 13. I'm going to put that down here. We have 1, 1, 1, 0, which is 14. 1, 1, 1, 1, which is 15. And back to 0, 0, 0, 0. So you can see why in this one, because of these propagation delays, we want to sample at least at the halfway point, because usually by then, or hopefully by then, they'll all have changed states. So what we have here is an up counter, counting from 0 to 15, and then recycling and starting over at 0 again. Now we have exactly the same circuit, but now we're calling it a frequency divider. So let's see why it's called a frequency divider. So we know from before that frequency is defined as 1 over the cycle time. So for our clock, for example, we have 2 squares here for each cycle. So let's assume 1 square is half a millisecond. That means our clock cycle takes 1 millisecond. So if we take that 1 over 1 millisecond, which we have here, so the frequency of the clock is 1 over 1 millisecond, that gives us a clock input of 1 kilohertz. Now let's look at Q0. We can see it takes 1, 2, 3, 4 cycles, or 4 squares, to make 1 cycle. So 4 times half a millisecond gives us 2 milliseconds. So the frequency of Q0 is 1 over 2 milliseconds. And that's going to give us a frequency of 500 hertz. Now if we look at Q1, it's taking us 8 squares, or 4 milliseconds, for each cycle. So now we have 1 over 4 milliseconds, or 250 hertz. For Q2, we have 16 squares. 16 times half a millisecond each gives us 8 milliseconds for a cycle time. 1 over 8 milliseconds gives us 125 hertz. And finally, for Q3, we have 32 squares here. 32 times half gives us 16 milliseconds. 1 over 16 milliseconds gives us a frequency from our last output at 60, what do we have here, 67.5 hertz. So you should be able to figure out why now it's called a frequency divider, because each time we add another flip-flop as we go from the clock to our output Q1, our frequency is half of what we had before. We add another flip-flop, it halves again. We add another flip-flop, it halves again. Another flip-flop, it halves again. So we have now divided that initial clock frequency down to a much slower frequency. So let's summarize that information about mod counters or frequency dividers. Remember, it's exactly the same circuit. The inputs of a JK flip-flop are wired to toggle, and the output is connected to the clock of the next flip-flop. The very first flip-flop has its input driven by the original clock signal. So if we have one flip-flop, it means we have two counts, 2 to the 1, and that count is 0 to 1. If we have 3 flip-flops, we have 2 to the 3 or 8 counts. The range of counts is between 0 and 7. So what's important to remember is if we have n flip-flops, we have 2 to the n different values, and the range is going to be 0 to 1 less than the number of different values. If we look at that same circuit in a role as a frequency divider, if we had one flip-flop, then the output of that flip-flop is going to be half of what it received coming in. So if we have 3 flip-flops in sequence, based on the clock signal, it's going to be 1/8 or 1 over 2 to the 3 of that input clock frequency. If we have 4, it's going to be 1/16 or 1 over 2 to the 4 of that input frequency. So the important thing to remember, with n flip-flops, we have 1 over 2 to the n times the input frequency or the clock frequency.